Hello everyone, welcome to the fifth class of this course. So in the last class what we did is we took a second order differential equation and we found the series solution at an ordinary point. So in this class we will also we'll do a similar kind of thing, like we will write down a differential equation and try to find out series solution at some ordinary point. Okay, so this is example 2. Okay, so the given differential equation is y double dash or d2y dx2 minus 4x y dash, that means dy dx, plus 4x square minus 2 times y equals to 0. Okay, and we are asked to find out series solution of this differential equation. So find out the series solution at x equals to 0. Okay, if the solution exists. So in that case we can see that, okay, this is the px which is 1, this is the qx equals to minus 4x, and this is the rx which equals to 4x square minus 2, and it's very easy that px is not equals to 0, and that means basically qx by px which is minus 4x is analytic at x equals to 0, and also rx by px which equals to 4x square minus 2 is also analytic at x equals to 0, and as a result x equals to 0 is an ordinary point for the given differential equation. Okay, and as it is an ordinary point, we are expecting the solution as y equals to an x minus x naught, and x naught is 0. We are asked to find out the series power series solution at 0, so that means x minus x naught to the power n, and as x naught equals to 0 I can simply write it as x to the power n. So this is how the solution will look like, where n equals to 0 to infinity, and our job now is to find out these ans. Okay, so find out these ans, that's our job, right? Okay, so if y equals to sum over an x to the power n, then y dash will be dy dx, which is sum over n equals to 0 to infinity an times n times x to the power n minus 1, and I can write it as n equals to 1 to infinity, because 0th term contributes nothing, because here n is here, and if I put n equals to 0, then the 0th term will be 0 because of this n sitting here. and as a result I can start the series from n equals to 1, and the series will be minus 1, and y double dash will be equals to sum over n equals to 1 to infinity. If I do the second order derivative, another derivative of this y dash, then it will be n times n minus 1 an x to the power n minus 2 equals to sum over of n equals to 2, because n equals to 1th term contributes nothing. Just because n minus 1 factor is sitting here, if I put n equals to 1, in that case it will be 0. So I can start from n equal to 2 without any harm. So it will be n minus 1 an x to the power n minus 2. Okay. Yeah. So now what we can do is basically we can shift the index for y double dash. So for y double dash, if we shift the index, it will be n equals to 0 to infinity n plus 1 n plus 2 a of n plus 2 x to the power n. Okay, so this index shift method, I mean here x has a power of n minus 2, and I want x to have a power of x to the power n, right? I want x to have a power of n, just because we want to do the power comparison, comparison. So this transformation, how the index shift is done, that we already showed in previous classes, I mean more than once. So I can give you a hint, like if I take m equals to n minus 2 and then just replace, take care of the limit, like and then replace n by m, then you will basically get this series. Okay, I'm not doing it again. Okay, so this will be one term, like, okay, so this will be one term, this will be the first term. Okay, this one. The second term is minus 4x y dash. Second term is minus 4x y dash, and we know y dash equals to this, right? So if I write it, then it will be minus 4 sum over n equals to 1 to infinity n an x to the power n, right? Because here it was x to the power n minus 1, and if I multiply it with another x, it will be x to the power n, right? So this is the second term, this is the first term, this is the first term, and this is the second term. Okay, so in the second term we have x to the power n, so we don't need to do the index shifts, right? We can directly compare from here. And now let's look at the third term, which is this one, right? So the third term is a bit tricky. So it is 4x square minus 2 times y. So it is 4x square minus 2 times y. This is the third term, right? Okay, let's see. So what we assumed as y is sum over n x to the power n. Okay, so it is 4x square minus 2 times n equals to 0 to infinity an x to the power n. Good. Now we got two terms, so that means which is basically the first term will be 4 n equals to 0 to infinity an x to the power n plus 2, because of this x square we have, and the second term is basically minus 2 sum over of n equals to 0 to infinity an x to the power n. Okay, so now this term, it has a, like, it is x to the power n, right? X is a power of n, so we are not bothered about this term. So here we are already done. But this term, if you look at it, it has a power of x to the power n plus 2. So here we need to do the index shifts. Okay, cool. So now to do the index shift for only for this term, okay, so only for this term. So what we will do is n equals to 0 to infinity n x to the power n plus 2. Okay, only for this term we will do the index shifts, and we want this series to write as x to the power n, right? So in that case we will assume that m equals to n plus 2. Very simple. In that case n will be equals to m minus 2, and if n equals to 0, m equals to 2, and if n tends to infinity, m also tends to infinity. So in that case this series I can write it as m equals to 2 to infinity, because n equals to 0 means m equals to 2, and n tends to infinity means m tends to infinity. So I am replacing n by m, okay, and this n equals to m minus 2, so it will be a m minus 2 x to the power m, because n plus 2 is m, right? M plus 2 is m. Good. So now as m is a summation index, I can write it as n equals to 2 to infinity a of n minus 2 x to the power n, and we are done. Okay, so basically the third term in the differential equation, which was 4x square minus 2 times y, that will be equals to 4 times, so only this part we have written here, so there will be 4 multiplication multiplied with it, so it will be 4 times this term, okay, so it will be 4 times n equals to 2 to infinity a n minus 2 x to the power n. Good. And then the other term, which is minus 2 sum over a n x to the power n equals to 0 to infinity. So these are the 3 terms of the differential equation: this one, and this one. So let's put them together. So the first term is y double prime. Okay, so the equation is y double prime minus 4xy prime plus 4x square minus 2y equals to 0. This was our differential equation. So let's put the values we calculated. So y double prime is this term, right? This term. This is sum over n equals to 0 to infinity n plus 1 n plus 2 a n plus 2, okay, a n plus 2 x to the power n. So the second term is minus sum over n equals to 1 to infinity, okay. Second term is this term. Second term is this one. So minus 4 n equals to 1 to infinity n a n x to the power n, okay. So minus 4 n equals to 1 to infinity n a n x to the power n, okay. And now the third term, which is this one. So it will be plus 4 sum over n equals to 2 to infinity a of n minus 2 x to the power n minus 2 n equals to 0 to infinity a n x to the power n equals to 0, okay. So these are the 4 terms. Now we can see that, okay, for all of these 4 summations, x has a power of n. Okay, but can we put them together? No, it's because you can see the summation. So here it is starting from n equals to 0, here it is starting from n equals to 1, here it is from n equals to 2, and here it is again from n equals to 0. Okay, so what we will do is basically we will write this series where all the summation terms will start from n equals to 2. And how we will do that? Simple. So let's take this term, this summation term, and let's write the first n equals to 0th term. So if I just write this series, then it will be the n equals to 0th term is basically 1 multiplied with 2, so it is 1 multiplied with 2, that is 2, a2, and x to the power 0, that is 1. Okay, so n equals to 0th term is 2 a2. Good. N equals to 1th term is, if I write it, plus n equals to 1th term, which is 2. If I put n equals to 1, so here if I put n equals to 1, it will be 2 times 3, that is 6, times so 2 times 6. If I put n equals to 1, 2 times 3, it will be a3, and it will be x, right, because x to the power 1. Okay, so this term will be 6 a3 x. Good. And then from n equal to 2, I can write the whole series. So n equals to 2 to infinity. This is the n equal to 1th term, this is n equal to 0th term, and now after that I am writing it as a summation. N plus 2, n plus 2 to the power. Very simple. This is the first series, this series, which was initially starting from n equals to 0. Now it looks like this. Okay, good. Now this first, now let's look at the second series. The second series is starting from n equals to 1, but we want to start all the summations from n equals to 2. So let's separate out n equals to 1th term. Okay, the first term will be, if I put n equals to 1, then it will be minus 4 a1 x, right? And all the other terms, like I can write it, then the other terms will be 4 n equals to 2 to infinity n x to the power n. Good. So then this term already is starting from n equals to 2, so I will write it as it is, which is a 4 n equals to 2 to infinity n minus 2 x to the power n. Good. And this last one, it is starting from n equals to 0, right? But we don't want that. We want it to start from n equals to 2. Okay, but we don't want to change this fact x to the power n also. So in that case, what we will do is we write similarly, we write the 0th term, which is minus 2 a0, the first term, which is minus 2 a1x, and then we will write the summation, which is basically minus 2 sum over n equals to 2 to infinity an x to the power n equals to 0. Fine. So this this whole series, which was initially starting from n equals to 0, now looks like this. This is the 0th term, this is the first term, and the rest of this term are written here. Good. So now what we will do is, the constant term we will put it in a bracket. So the constant terms are this term, so and this term. Okay, yeah. So what we have is basically 2 a2 minus a0. Okay, now the terms which are multiplied with x to the power 1, those terms I will put together. So this term, and this term, these are the three terms. Okay, which has, x, where x has a power of 1 basically. So this I can write it as plus 6a3, okay, and here is minus, so there is 4a1 and here another is minus 2a1, so minus 4a1 and minus 2a1, so we have minus 6a1, right, minus 6a1 whole x, right, and I can take this 6 outside, so this I can write it as 6 here. Good. Or let me write it 6a3 minus a1 times x, right, and then we have all the other terms, which is plus n equals to 2 to infinity, so this term, this term, this term, and this term. So what we are left with is basically n plus 1, n plus 2, a of n plus 2 minus 4 n plus 2 times an. Okay, so I'm combining these two terms, so this I'm combining this one and this one, so that we got here. There is, so if I take this 4n, so take the an common, then this minus 2 is coming from here, this is minus 2, okay, this term, and this minus 4n for this term, good. So these two terms are taken care of, okay, this term, and this term, and we are left with only this term, which is plus 4 an minus 2 times x to the power n equals to 0. Good. Yeah, fine. So now what we will do is, basically we will do so as this as this right hand side is 0, we will make all the coefficients equals to 0. So so if we do that, then what we have is basically, for the first one, for this term, for the constant term, we have a2 minus a0 equals to 0, which implies a2 equals to a0, right? So let me call it equation 1. If I make the coefficient of the second term x to the power 1 equals to 0, then we are left with a3 minus a1 equals to 0, which implies a3 equals to a1. Okay, let me call it equation 2. And for all other terms, so now for all n greater than equals to 2, what we have is basically this term equals to 0, right? So it's n plus 1, n plus 2, an plus 2 minus 4n plus 2 an plus 4 of an minus 2 equals to 0. And this relation will give us the recurrence relation. So how the recurrence relation will look like? It will be n plus 1, n plus 2, an plus 2 equals to, if I take these two terms in the right hand side, then it will be equals to 4n plus 2 an minus 4 an minus 2, right? And if I take another step forward, then it will be an minus 2 equals to 4n plus 2 divided by n plus 1 times n plus 2 times an minus 4 divided by n plus 1 n plus 2 an minus 2. So this is now our recurrence relation. Let me call it equation 3. So now this is our recurrence relation. So now let's look at this recurrence relation. It's very interesting. So what it says is basically, if we are given n minus 2th term and nth term, then we can find out n plus 2th term. Okay, so it's like, it's not like if we are given one term and then we can find some next term. So we need, two previous terms to find out one next, next term basically. So let me write it like this. Okay, so let's say this is a0, this is a1, a2, a3, a4, a5, a6, a7, a8, a9, a10, dot 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 dot, all the other coefficients. So our primary goal is to find out these, a1, a2, a3, ai's basically. Okay, so if we can find those ai's, these ai's, these an's, we will find the solution. Great. So to start with, what we have is basically, if we start with a0, for example, let's say we start with a0, so then from equation 2 we know a2, right? And for the other, if one starts with a1, then from equation 2 we know a3. So if one starts from a1, then from equation 2 a3 is known, right? And now this recurrence relation is valid for n greater than equals to 2. Okay, so it for n greater than equals to 2. So let's put n equals to 2 in this recurrence relation. What it gives? So it gives a4. So let's put, okay, let me again divide it in two parts. So what we have is basically we are starting with, okay, let me use green color. We are starting with this a0, okay, and we know a2, which is equals to a0 from equation 1, right? And now in this recurrence relation, if we put n equals to 2, so in this recurrence relation, if we put n equals to 2 in this recurrence relation, what we have is basically a4 equals to so n equals to 2 means 4 times 2 is 8 plus 2 10. It is 10 divided by 2, which is basically 3 times 6, right? 3 times 6, sorry, 3 times 4, so it is 3 times 4, that is 12. Okay, times a2, n equals to 2, so a2, good, minus 4 divided by n equals to 2, that means it is 3 times again 4, that is 12, and if I put n equals to 2, this is a0, right? an minus 2 is a0. So this is 3, this is 5 by 6. Okay, and now what we know is basically a2 is a0, right? So a2, so what we got here is interesting. So we got a4 in terms of a2 and a0, right? So from a2 and a0 we got a4, we got a4. And now if I write, so here we know that a2 equals to a0, so if I write it here, then it will be 5 by 6 a0 minus 1 by 3 a0, which equals to, yeah, so it is 5 by 6, it is 5 minus 2 divided by 6 a0, which is, so 5 minus 2 is 3, 5 minus 2 is 3, which is half. So basically what we have is basically a4 equals to half a0. Good. So this is good. And okay, so now for the other series, if one starts with a1, then from equation 2 he knows that a3 equals to a1. Okay, like if one starts from a1, okay, from equation 2 he knows that a3 equals to a1. So basically one knows a3 and a1. And now if I put n equals to 3 in this recurrence relation, what we have is basically a5 equals to 4 times 3 is 12 plus 2 14 divided by 3 plus 1 is 4 and 3 plus 2 5, so 4 times 5 20 a3, good, 20 a3 minus 4 divided by 20 a0, sorry, a1, right? Because n equals to 3 and n minus 2, an minus 2, that means a1. And so here you can notice that a5, we can find a5 in terms of a3 and a1. So if one knows a3 and if one knows a1, so then we can get a5. Right, and I can simplify it, so it will be 20 by 10 a1, which is half a1. Okay, so now if I put n equals to 4, what we get? If I put n equals to 4, then it will be a6, right? So a6 equals to, so it will be a6 equals to 4 times 4 16 plus 2 18 divided by 5, 4 plus 1 5 times 6, so 5 times 6, 5 times 6, and n equals to 4, so a4 minus 4 divided by 5 times 6 a2, right? So n minus 2, an minus 2, so an minus 2, n equals to 4, that means it is a2. So what this relation tells us that if one knows a4 and a2, then he can find a6. So in this line it basically says that okay, if one knows a4 and a2, then you can find a6. Now I think the recurrence relation is making sense. And okay, if I put a4 equals to a0 by 2, so then it will be 9 by 5 times 6 a0 minus 4 5 times 6 a2 a2, and a2 is a0, right? So we know that a2 is a0. So in that case it will be a0. It means 5 times 6, and then 9 minus 4 is 5, a0, which means a6 equals to this 5 cancels, and we are left with 1 by 6 a0. Now if I put n equals to 5 in this recurrence relation, if I put n equals to 5 in this recurrence relation, we are so what we will get is basically a7. Okay, so if I put n equals to 5, then an plus 2 is a7. So a7 equals to, okay, 4n. So 4 times 5 is 20 plus 2 is 22. So 22 divided by 5 plus 1 6, and then 7. So 6 times 7, 6 times 7 multiplied with a5 minus 4 divided by 6 times 7 a3, right? These two terms are same basically here, n plus 1 n plus 2, so that's why I wrote them as 6 times 7, and 4 is a constant here sitting, and an minus 2, n is 5, so in that case it is a3, n minus 2 is 3. Good. So what this relation tells us that okay, if you give me a5 and a3, then I can tell you a7, right? So what it says basically, if you give me a5 and if you give me a3, then a7 can be determined. So let's calculate a7. Okay, a5 is half a1, right? A5 is half a1. So if I write a5 as half a1, so in that case it will be 11 times 6 times 7 a1 minus 4 6 times 7 a1, because a3 equals to a1, no? A3 equals to a1, right? So what we have is basically 6 times 7 and 11 minus 4, and 11 minus 4 is nothing but 7. A1 implies a7 is 1 by 6 a1, and this is how the series will proceed. So like now if I put n equals to 6, so if I put n equals to 6, then I will get a8. If I put n equals to 7, then I will get a9. Okay, a9 equals to something, and then it will proceed. I will find the other terms. So what this recurrence relation says is basically, if we are given two consecutive terms, two consecutive event terms for this series, green one, then I can tell the next event term. And if we are given two consecutive odd terms, then I can tell the next odd term. So that's the relevance of this recurrence relation. Okay, so in previous examples, the recurrence relation were like, if you are given one single term, then I can tell the next term, another term. But here we need to provide two terms, to get one new term basically. So I mean, in this way the series will proceed. Basically, if we want to find A8, then we need A6 and we need A4 also. Then only we can find A8. So in case of A9, we need A7 and we need A5 also. Then we can find the A9 and so on. So basically we are left with two series. One is for A0, the series of this even even coefficient even indexed coefficients, and this is the series of odd indexed coefficients if one starts with A1. So the general solution will be y, which will be A0 plus A1x plus A2 x square plus A3 x cube plus A4 x to the power 4 plus A5 x to the power 5 plus dot dot dot. Okay, and we know that, okay, I can separate it in two series, which is A2x square plus A4 x to the power 4 plus dot dot, all the even indexed terms, plus the odd one, that is A1x plus A3x cube plus A5 x to the power 5 plus dot dot dot. Okay, and if I write these values, like if I write A0, I mean for all these terms like A0, A2, A4, where A0 will be common, I mean I can write A4 in terms of A0, I can write A2 in terms of A0, right? So I can put A0 outside, and then it will look like 1 plus A2 is A0, that means it is x square, plus A4 is half A0, so that means it is half x to the power 4, plus A6 is 1 by 6 A0, that means 1 by 6 x to the power 6 plus dot dot dot. Okay, plus this is for the even power of x, and for the odd power of x I can take A1 outside, and then it will be x plus A3 is A1, right? So it will be x cube plus A5 is 1 by 2 A1, right? So it will be 1 by 2, A1 is outside, so that means x to the power 5, right? And the next term is 1 by 6 A1, A7, so that means it will be A7 x to the power 7, and A7 we know that it is 1 by 6 A1, right? So A1 is already outside, so it will be 1 by 6 plus dot dot dot. So this is the general solution for x. So I can write it as, one series as y0x and the other one as y1x. Okay. Okay, I am using different colors. This one is green. This is y0x. This is y1x. So basically the solution will look like yx equals to a0 y0x plus a1 y1x. So these are the two linearly independent solutions, y0x and y1x, and the general solution is basically the linear combination of these two independent solutions, and these are the arbitrary coefficients. So there are two like arbitrary coefficients or constants. It's because we have a second order differential equation. Okay. So this is how we will solve and find a series solution of a second order differential equation around some ordinary point. And now some exercises you can try. So let me give you some exercise. Exercise 1, which is find the first 6 terms of the series solution at x equals to 0 for, okay, let me write it like this. For number 1, x square plus 1 y double dash minus 4x y dash plus 6y equals to 0. Number 2, so you can try these problems at home. I will not solve them. So these will be similar to the 2 problems you already solved. X square plus 1 y double prime minus 2x y dash plus 2y equals to 0. And the last one, this you can try. I will expect you to try 1 minus x square y double dash minus 2x y prime plus L into L plus 1 y equals to 0. Okay, this L is a constant. So you can try these 3 problems. I would expect you to solve this one, and this you can try, give it a try. So first, what you need to show is basically x equals to 0 is indeed a ordinary point. That you can very easily show. You can take this term as px and show that, okay, it's not equals to 0 at x equals to 1. It's x equals to 0, sorry. And then you can take the solution as y equals to sum over a n x to the power n equals to 0 to infinity, and follow the usual procedure to get the solutions, to find the a-n's. So these 3 problems you can try. Okay, so that's all for today. In the next class, what I will do is I will take a differential equation and try to find the series solution at a regular singular point. So basically I will use the Frobenius method. Okay, so that's the goal of the next class. So related to the Frobenius method, I will solve two or three, maybe 2 problems I will solve, and then I will move to the Legendre polynomial. So this differential equation, the last one, it is basically a Legendre differential equation. So I will, when I will be solving and finding the Legendre polynomials, I will be solving this differential equation. But before that, I want you guys to try. So that's the reason I am giving it. Okay, so that's all for today. Bye.